This data model plots the Chi 2022 formula for lithic degradation. It establishes a strict physical rule. When the mass loss ratio of sandstone reaches a 5% threshold, macroscopic cracking, block shedding, and collapse begin. We apply this exact metric to the Yungang grottos. Assuming construction occurred 1,500 years ago, from AD 450 to 520, the carved sandstones were fresh. Running this calculation forward produces a specific timeline. Under this model, the grottos began to destruct in AD 800. The predictive model drives toward a singular conclusion. Under natural conditions, these structures will face absolute annihilation in 4,000 to 5,000 years. Yet physical reality contradicts the computational timeline. The massive facial features of the Yungang Buddhas remain intact today, standing centuries past their mathematical expiration date. This discrepancy forces a forensic data audit. Either our geotechnical weathering models are flawed, or these megalithic structures possess unaccounted systemic defenses. The dossier of systemic paradoxes identifies specific, localized architectural anomalies that defy baseline environmental exposure rules, beginning with hydraulic dissipation at the Leshan Giant Buddha. The excavation of this 71-meter sandstone rock mass actively reduced river turbulence and altered hydraulic shear stress at the confluence of three massive rivers. A second paradox exists in Guizhou province, categorized as the erosion immunity of fanjingshan. Twin temples sit perfectly balanced on an isolated 100-meter metamorphic rock pinnacle. They endure extreme wind shear and freeze-thaw cycles without any measurable structural slippage. To understand how these anomalies persist, we must abandon macro-environmental assumptions and interrogate the exact lithological and machine learning dynamics of their host rock. We begin by interrogating the structural integrity of red continental clastic rocks subjected to cyclical, chemical, and dynamic stress. Laboratory protocols simulate corrosive environments using exact experimental parameters: 0.1 mole per liter ion concentration across pH levels of 2.5, 4.5, and 7.0. The chemical degradation mechanism operates at the molecular level. Hydrogen ions react with active minerals inside the rock, like carbonates and iron aluminum oxides. This reaction triggers a mechanical failure cascade. The dissolution of cementing substances induces particle instability, rapid pore enlargement, and microcrack merging. This schematic illustrates the computational dataset sourced from 597 tests using the split Hopkinson pressure bar apparatus to measure dynamic compressive strength, or DCS. The ensemble learning algorithm processed 5 exact input variables: strain rate, number of wetting-drying cycles, pH, uniaxial compressive strength, and P-wave velocity. The XGBoost and LightGBM models provided the highest predictive accuracy for calculating exactly when the rock will shatter under high-strain dynamic loading. This chart displays the SHAP value distribution, isolating how each variable drives structural failure. The machine learning model isolated a singular truth: strain rate is the most influential factor in DCS prediction, whereas uniaxial compressive strength contributes relatively less. The data proves that high strain rates rapidly trigger macroscopic failure. To counter this, the builders of the Leshan Buddha finalized a multi-tiered internal drainage and ventilation system over 90 years. By regulating internal moisture, they effectively throttled the moisture-driven pressure cycles that lead to the dynamic failure we see in the model. Moving from continental red sandstone, we pivot to the marine carbonate limestone host rock of the Longmen grottos. Here, the degradation is biological. Cyanobacteria serve as the foundational autotrophic engine and primary organic carbon producers across the surface of the monuments. These organisms drive the critical biochemical mechanism responsible for severe deterioration in these specific grottos: nitrification. This flowchart maps the exact chemical reaction. Nitrifying bacterial consortia oxidize ambient ammonia, synthesizing highly corrosive nitric acid directly on the stone. This biogenic nitric acid instantly reacts with the calcium carbonate substrate of the limestone, causing rapid dissolution. This microbial acid corrosion represents the primary pathway of irreversible mineral loss at the site. The biological colonization of the rock creates a self-sustaining acid factory. This microscopic chemical decay determines the monument's lifespan as surely as macro-scale wind and rain. We can observe a cross-site environmental filtering comparison by analyzing the clay-rich siltstone of the Meijishan grottos. Meijishan's microclimate features persistent monsoon-driven high humidity, maintaining a relative humidity greater than 70% for over 180 days a year. This specific humidity threshold acts as an environmental filter, heavily favoring the proliferation of hydrophilic actinobacteria. Pseudonocardia and actinomycetospora act as the dominant colonizers, actively modifying the local pH to construct slightly alkaline, destructive microenvironments. Contrast this with the arid climate of the Mogao grottos, where the relative humidity stays below 70% for over 240 days a year. This extreme aridity selects completely different metabolic strategies, allowing zero-tolerant firmicutes to achieve ecological dominance across the rock face. To survive, they execute a precise defense mechanism, forming multi-layered protective endospores to resist severe desiccation, with Rhodococcus operating as the core genus. Despite these extremes, the atmospheric biological load for these sites is regulated, maintaining a mean air microbial concentration of 754 CFU per meter cubed for bacteria and 645 CFU per meter cubed for fungi. This taxonomic divergence proves that heritage conservation cannot rely on standardized chemical treatments. Interventions must be precisely targeted against the site-specific metabolic pathways dictated by local humidity. The forensic audit shifts to the extreme arid geomorphology of the Yadon landforms in Xinjiang, known as Mogucheng, or Devil City. These yardongs exhibit a cyclic sedimentary structure formed by an alternating deposition of hard carbonate-cemented aqueous layers and soft, loose aeolian sand layers. This diagram displays a chronochromatic analysis mapped across the YA and YB stratigraphic profiles, analyzing the yellow, brown, green, and red hues as direct paleoclimate proxies. The extracted chemical metric is exact. Organic matter content is the main factor affecting brightness, while iron oxide directly affects the sediment redness and yellowness. Yet the structural layering of Mogucheng produces an anomaly outlined in Dossier Layer 3, extreme acoustic shrieking. The precise geometric, high-density alignment of these specific eroded clay pillars acts collectively to create highly targeted Helmholtz resonance channels across the desert. The exact geometric alignment required for Helmholtz resonance mimics manufactured acoustic chambers. This structural precision forces us to ask if aeolian erosion alone can account for this architecture. Synthesizing these core findings presents an uncompromising truth. Both the computational XGBoost predictions and the biogeochemical microbial decay models confirm that absolute structural collapse is mathematically inevitable. However, remote sensing and LiDAR scan mapping conducted between 2020 and 2026 across the Longmen and Yungang cliffs reveal a conflicting modern reality. This radar cross-section reveals deep artificial void cavities located directly behind the major Buddha statues. These voids function as structural counterweight chambers. By hollowing the rock, engineers diverted vertical stress, routing the mountain's weight into the solid surrounding bedrock. This application of load-force redistribution points toward an empirical understanding of the stress relief we are only now mapping with LiDAR. The carvers engineered a physical workaround to the failure models we rely on today, possessing an early grasp of dynamic compressive strength. While the architectural anomalies hint at advanced engineering, the macro environment offers active, chaotic environmental edge cases that refuse any comforting resolution. Massive magnetic disruption zones dictate the specific uninhabited basins in Ho Shil. The geological data suggests that the localized geomagnetic fluctuations that disrupt satellite GPS telemetry are caused by deep-seated basaltic volcanic intrusive bodies. The final and most impenetrable anomaly exists inside the cryptozoological and microclimate zones of the Shenangjia Virgin Forest. Shenangjia's dense canopy creates localized inversion zones where temperature and atmospheric pressure deviate from regional baselines. These hyper-localized microclimates invalidate macrogeological rules, preserving uncatalogued flora in an environment that shouldn't exist.